Now for number 1, we can't use arctan because we have an x up in the numerator. Do we have u prime over u? We would if we had a plus 2 in the numerator. So what if we do that? What if we actually plus 2 in the numerator and also minus 2? Now I'm going to split this fraction. Our first integral would be ln of u, absolute value u. For our second integral, I'm going to actually factor the denominator. Hey, notice that the denominator is a perfect square trinomial? Now I can use the general power rule for integration. I'm also going to factor the inside of the log argument. Using the properties of logs, I can bring the square down as a coefficient. And if this were free response, you could have stopped once you finished your integration. Oftentimes, trig identities can help you integrate. So tangent squared of x equals secant squared x minus 1. So if you have tangent squared of 2x, I'm going to turn that into secant squared 2x minus 1. Cotangent squared 3x will be turned into cosecant squared 3x minus 1. The integral of secant squared is tangent, but it would be secant squared u prime, so we need a 2 and a 1/2 here and a 3 and a 1/3 here. And there's your answer. We did an example a while ago of the integral of an absolute value and how you can split that integral into separate ones and take care of the signs. This graph is x squared minus x minus 6. So if I were to graph the absolute value version, any y value above the x-axis stays, any y value below is reflected. This splits our integral into 3 sections. From -3 to this first intersection of -2, our area will be positive. We'll just use the regular x squared minus x minus 6 function. Now the integral between -2 and 3, if I'm using the non-absolute value version of this parabola, that is going to give me a negative area. But since I'm using the absolute value version, I need this negative area to become positive area. So I want to change the signs for this in-between integral. The rest of the area follows the non-absolute value version of the parabola, straightforward as positive area. And there we have our integral setup. For number 4, we have a fraction, but our denominator is a monomial. So I'm going to divide each term in the numerator by that monomial. For the first one, I want to see if I have sine u prime in my integrand. Hey, look at that. We're just missing the -3 in the numerator. Now we have sine u prime in the integrand, so the integral of that is cosine of u. We can simplify this to be e to the -2x. And if we are integrating e to the u prime needs to be present, and that would be a -2. Usually your answers shouldn't have negative exponents, but when e is the base, they'll usually just leave it as a negative exponent. Let's try using maybe some trig identities that could make our lives easier. So what if I made u the part with the ln? If you used, you don't have to substitute in the u's, but I'm going to do it just so you can see the visual. We would have u to the power of 2 cotangent x dx, that is du. Your integral just adds 1 to the power and then substitute u. And you'll get 1/3 ln sine x quantity cubed. Remember that if integrals involve radicals and you can't seem to fit the integrand into any basic integration form, you should try u-substitution. I'm going to make u the radicand. Substitute your u's. And there's your answer.